Swayam Prabha. Digital India. Educated India.
Hello everyone. Today we will continue our discussion on the theory of electron transport through the Mosfet, and as you might recall that in our previous class we concluded the discussion on the traditional way of deriving the IV characteristics of the Mosfet, and we started with the understanding the electron transport theory in the nano MOSFETs. Okay. So, let me quickly summarize what we have seen so far, and you might have seen this slide earlier as well. So, the basic understanding of the MOSFET can be done in terms of this energy barrier device. So, the MOSFET can be visualized as a device which has a barrier in the energy landscape in the channel. So, the electron sees a barrier in the channel, and by changing the voltage on the gate terminal, this barrier can be manipulated, and similarly by changing the voltage on the drain terminal, we can create asymmetry around the barrier and facilitate the current flow. So, this is this plot which you see here. This is the plot of energy as a function of x, and the energy is the conduction band energy, the bottom of the conduction band energy here. And this is an extremely important plot, I would say, in order to properly understand the physics of the MOSFET. Okay. So, please keep this in mind that when we have a gate voltage and a drain voltage applied on a MOSFET, this is how the energy landscape of the MOSFET looks like. And this point here, which is the point right at the beginning of the channel, this point, which is also the peak of the barrier, is an extremely important point, and generally it is under the weak influence of the drain voltage and under the strong influence of the gate voltage. Okay. And that is the essence of functioning of the MOSFET, because if this point is also under the influence of the drain voltage, in that case there would be a huge variability in the system, because this DIBL effect will be there and the threshold voltage will not be properly defined, cannot be properly defined, it cannot be defined just in terms of the gate voltage, and that is what this scenario, that is not what we do not want. So, we have seen the subthreshold swing, we have seen how do we traditionally define the IV characteristics of the MOSFET in terms of IDS, in terms of VDS and VGS, and how do we calculate the electric field in a traditional MOSFET from the current expression. Okay. But we also saw that this generally this equation is not valid if we go to nano MOSFETs or ballistic MOSFETs, because in that case this notion of mobility is not defined, and we might need to consider the ballistic transport. So, we need to invoke the general model of transport in order to properly understand the MOSFET physics. So, that is what we will see, and that this transport theory is also known as the Landauer transport theory of the MOSFET, because it was initiated by Rolf Landauer. He was the first person to formulate or to calculate the quantum of conductance in a MOSFET, and then this theory was developed by Professor Supriyo Datta and Professor Mark Lundstrom from the Purdue University, and that's how we also try to understand this in this part of the course. Okay. So generally in this approach, what we have is we have a left contact. In between we have the device region or the channel region, and on the right side we have a right contact. So this is source, this is drain, and this is the channel region. This is the case with the two terminal device, but in a MOSFET, in addition to these two terminals, the source and the drain, there is a third terminal as well, which is known as the gate terminal. Okay. So the way things now can be defined here is that if we plot the electronic energy states in this device, on the left side, so generally we assume that the source and the drain are bulk regions, they are pretty much like bulk regions. So we can define the Fermi levels for the source and the drains. So we can define Fermi level for the source EF1, let us say, and Fermi level for the drain EF2 or sometimes EFD as well. The channel is a small channel. In modern day MOSFETs, it's only just few tens of nanometers. So we need to define the electronic energy states in the channel, and the distribution of electronic energy states is defined by the density of states in the channel. And since the channel is small, these states can be discrete states as well. And at some places there might be some gap in the energy landscape, some of the energies may be disallowed for the electrons. So for example, this range of energy is, let us say, disallowed. Generally the voltage on the source side is fixed, this is grounded, so this EF1 also stays fixed, and generally a drain voltage is applied in the system. So we put a battery sometimes here, and that's how we can change, and that's why this EF2 can change and this EF2 may come down. So if a positive voltage is applied, EF2 will come down and this will change by minus QVD. Okay, so this is the EF2 after the voltage has been applied on the second terminal. Okay. Okay, so this is the difference between EF1 and EF2. Now this gate voltage, as you might have guessed by now, by changing the voltage on the gate terminal, we can change electric field or potential in the channel, and if the potential is changed in the channel, it means that the potential energy of the electrons can also be changed. So what this does is, this gate voltage here, this can shift these electronic states up or down. So that's the major influence of the gate voltage. When the gate voltage is applied, these energy states that are there in the channel, all of them, they can either be shifted upwards or they can be shifted downwards. So if we are applying a positive voltage, they will be shifted downwards, and if we are applying a negative voltage, they will be shifted upwards. Okay. So that's the basic qualitative mechanism, that is what is happening here, and the source and the drain terminals are bulk terminals or quasi bulk terminals. So we can define the Fermi functions in these contacts F1 and F2, and Fermi functions tell us about the electronic distribution in the each of these contacts. Generally it is assumed that because of the inelastic scattering in the contacts, even when there is a current in the system, even when these Fermi functions, these distributions are maintained. Okay, so that is an assumption, and that's why we can use the notion of Fermi functions even when the current is flowing through the system. However, just to sort of point it out here, if the number of electrons that are traveling from the source into the channel is huge or is significant, and this number is comparable to the total number of free electrons in the source terminal, in that case this current might change the distribution significantly, and in that case we cannot use these distribution functions when the current is flowing in the system. But generally that is not the case. The source and the drain contacts are like bulk contacts. There is a huge number of electrons sitting in these contacts, and even if there is a current, it does not change the distribution significantly, and that is why we can use the notion of the Fermi functions in the even in the steady state when the current is flowing through the system. So that's what happens, and there is a basic point that I would just like to remind you, which we have also discussed several times during our discussion on the general model of transport, that what happens is when we apply a voltage on the drain terminal, the drain contact tries to bring the channel in equilibrium with the drain contact with itself, and the source contact tries to bring the channel in equilibrium with the source contact or with itself. What it means is that this source contact tries to fill all the electronic states in the channel up to source Fermi level, up to this energy level. And similarly, the drain contact tries to fill all the electronic states in the channel up to this energy level. So the energy states in between these energy states are the most interesting energy states, because the source is trying to fill them and the drain is trying to empty them, trying to take electrons out of them, and that is how a current is maintained in the device. So in the intermediate range of the energy states, the energy states that lie between EF1 and EF2, in those energy states the current conduction actually happens in a way. So that's what it is, and that's why in the current conduction this difference of the Fermi functions, this difference F1 minus F2 becomes the driving point, driving factor basically. And if you recall our discussion on the general model of transport, the current is given by this equation, where the current is a constant times the number of modes in the device and the difference of the Fermi functions integrated over all possible energy values. And if there is scattering in the channel, if the channel is a diffusive channel, in that case we also need to take into account the transmission coefficient. Okay. So this is a very straightforward expression in a way, because it takes into account this factor, this parameter ME. And what is ME? ME is the number of modes in the channel. And what are the modes? If you recall from our discussion on the general model of transport, modes are like conduction pathways in the channel. They are like lanes in the channel through which electrons travel in the channel. So it depends on the number of lanes in the channel times the difference in the Fermi functions, and this becomes the driving force actually. And this parameter TE accounts for the scattering in the channel. So ultimately, if we need to find out the IV characteristics of a MOSFET or a nano device or a ballistic MOSFET, this is the equation to start with actually. Okay, so this is the equation where we need to start with in nano devices, and for that we need to know the parameter ME, we need to know the parameter TE, and we obviously need to know the difference in the Fermi functions in the device. So the Fermi functions are defined as, So, for the left contact, this is the basic definition of the Fermi function, 1 plus exponential E minus EF1 by kT. And similarly, F2 Fermi function is defined as 1 divided by 1 plus exponential E minus EF2 by kT. So, the Fermi function, just to sort of remind you, is the probability that a state, electronic state at energy E is occupied by the electron. That is the probability and that is given by the Fermi function. So, this F1 tells us about the probability that a state in the left contact is occupied by the electron, and F2 tells us about the probability that the state in the right contact is occupied by the electron. So, in a way these are also the probability functions as well. And in the current equation, this parameter Te is the transmission coefficient, and it is also a function of energy E, because at each different energy levels the transmission might be different. Similarly, the modes might also be a function of energy. Generally, it is a function of energy. So, generally while discussing this model of transport, this Landauer model of transport, we first we try to understand what happens in ballistic limit and what happens in diffusive limit. And finally, if we can understand things in the diffusive limit, we can extend this diffusive limit idea to the long channel MOSFETs as well. So what we can in principle do is we can calculate the IV characteristics of the MOSFET from here if we properly know this TE, ME and F1 minus F2E, and if we integrate over proper energy range, then we can extend this IV characteristics to the traditional IV characteristics. Okay? But we cannot do vice versa. We cannot generalize the traditional IV characteristics and account for the ballistic regime. So, that is why this treatment is more fundamental. And I would also like to remind you one more point here, that this approach, this is not a purely quantum mechanical approach as well, because in this approach also the electrons are assumed to be I would say balls or like particles, still they are assumed to be particles, and but at the same time we are considering the quantized states of the electrons, we are considering the Fermi-Dirac distribution of the electrons, we are considering the effective mass. So, we are not solving the Schrodinger equation between the contact and the channel and between the source and the channel and the drain. We are assuming that it is like a particle, it may enter the channel or scatter back. So, that way it is not a purely quantum mechanical treatment. A pure quantum mechanical treatment will involve the solution of the Schrodinger equation in each case. Okay? In a given case, we would need to solve the Schrodinger equation for the. But this treatment is pretty much is fairly general as compared to the traditional treatment, and it can explain most of the electrical characteristics of the modern day MOSFETs. The MOSFETs which are few tens of nanometers in size, whose channel length is maybe 10 nanometer in size. Okay. So, so now generally in MOSFETs, if you recall, there is a linear regime of operation, and there is a saturation regime of operation. In linear regime, the applied voltage on the drain terminal, the applied voltage on this terminal is small, and in the saturation regime this voltage is actually large. So, there are two limits in which we finally need to discuss this equation. One is the small bias limit when the applied voltage is small, and one is the large bias limit. So, if we plot the energy states here, the energy states of the source, the drain and the channel, this is the Fermi function, this is the Fermi level EF1, Fermi function F1, drain side Fermi function F2, Fermi level EF2. Okay. So, and this is the applied voltage. So, if this voltage is large, then F1 minus F2 is actually equal to, almost equal to F1, and that is also clear from the plots of F1. So, for example, if we take, if we plot the Fermi function at 0 Kelvin, on the y axis if we have the Fermi function and on the x axis if we have the energy. So, at 0 Kelvin, if this is EF1, this is EF2, and at 0 Kelvin the Fermi level EF1, F1 will look like this. So, it will be 0 for all energy values less than EF1, and it will be, sorry, it will be 1 for all the energy values up to EF1, and it will be 0 above energy values EF1, and this is the Fermi function F1. Similarly, the Fermi function F2 will be this, and in this this EF1 is extremely larger than EF2, which means that this is far away from this, and this is maybe close to the origin or somewhere. So, then this F1 minus F2 can be approximated by just F1 fairly. So, in that case, this current equation, in this equation, this F1 minus F2 term can be approximated by the F1 term. So, that is the case, generally the case in saturation region of the MOSFETs in the large bias limit. And in the small bias limit, actually the small bias limit has been discussed a lot during the discussion on the general model of the transport. So, you might as well remember that in the small bias limit F1 is very close to F2, and this difference function can be approximated by a Taylor series expansion of the So, this can be approximated by this function. This is the small bias limit. So, in the linear regime of the MOSFET, generally this approximation will be used, and in the saturation regime of the MOSFET, generally F1 minus F2 can be approximated just by the F1 function. Okay, so, we are just trying to see how to use general model of transport which we had already discussed in the context of the MOSFET. Okay. So, yeah, this we have already seen that in the small bias limit this difference goes to this value, or sorry, there is this term Q times V as well here. So, instead of dE we have Q times V, where V is the applied voltage. And in the small bias limit we can define the conductance in a very clean way, because the conductance is defined as the ratio between the current and the voltage I by V, and in the small bias limit there is a very clean relationship between the current and the applied voltage, and this conductance is defined in this way. So, the conductance turns out to be 2q square by h integration of Te Me minus del f by del E dE, and this constant 2q square by h is the fundamental constant, and it is also known as the quantum of the conductance. Okay. We had a pretty comprehensive discussion on the conductance, so you can actually revise that if you need to. And finally, we have this Fermi window function actually. So, the Fermi window is generally applied, is generally used in the low bias limit. So, this function minus del f by del E, this is known as the Fermi window function, and it generally is the states between the two Fermi levels, between EF1 and EF2, which is pretty much clear. So, this plots on the left hand side, this plot is the plot of F1 and F2 for low temperature. On the right hand side, this is a plot of F1 and F2 at high temperature. Okay. And at low temperature, it is pretty much evident that this function F1 minus F2, which ultimately boils down to this, is essentially the states between EF1 and EF2. And at high temperature, this is slightly more complicated, and it is the states, primarily the states between EF1 and EF2, but some states out of that range as well. Okay. And here at high temperature limit, if you remember, we need to invoke the Fermi-Dirac integrals in order to do the proper calculation of the conductance and the conductance functions. So, so with this basic revision, we will see what is the transmission energy, transmission coefficient at a certain energy, or what is the transmission in the context of the MOSFET. Although we have had a discussion on the transmission in the general model of transport as well, but this number of modes can directly be taken from our previous discussion. Let us quickly try to understand the transmission in a MOSFET. In a MOSFET, generally, if this is the channel region of the MOSFET, if you remember, in the MOSFET generally the electrons are injected from the source side, they travel to the drain side, and I would say that the transmission is defined as the electrons received on the drain side as divided by the electrons injected from the source side. So, some of the electrons may scatter in the channel, they may travel back, they may change energy as well during the transport from the left contact to the right contact. So, that is why this parameter T is defined as the electrons received on the right side, on the right contact, defined by the electrons injected on the left contact. So, the left contact is taken to be x equal to 0 point, the right contact is taken to be x equal to L point. And let us see that the flux, which is the number of electrons per unit time coming on the left contact, is F plus x equal to 0. It is the flux at the left contact is this, plus means that the electrons travelling in the plus x direction, and the flux received at the right contact is F plus x equal to L. So, the transmission coefficient of the device will be defined as F plus x equal to L divided by F plus x equal to 0. Okay. And in the diffusive transport case, if you remember the derivation there, we apply a fixed law, we apply the fixed law basically, which looks like this. So, the flux that is injected on the left contact, all of that does not reach to the right contact, some of it may come back, and in fact what happens is that number of excess electrons on the left contact is generally, let us say if this is number of excess electrons is this on the left contact, Generally in long channels what happens is the number of excess electrons is on the right side is 0. So, this if we plot the number of excess electrons as a function of channel length, this is how it drops. So, on the left side it is Nx equal to 0, on the right side it is 0, and this is the channel length. So, the gradient of charge carriers in this device is becomes Nx equal to 0 by L, or this is the gradient, this is the negative gradient actually. If this is x equal to 0 point and this is x equal to L point. So, this becomes the gradient of the excess charge carriers in the MOSFET. So, by applying Fick's law, the net flux that is reaching to the right side becomes minus dN in terms of the diffusion constant dN times dN by dx. So, it becomes dN times Nx equal to 0 divided by L, and this is the flux reaching to the right contact. Okay, so, we have calculated the flux reaching to the right contact in terms of the diffusion constant. It turns out to be dN times number of excess electrons on the left contact divided by the length of the channel. And what is the flux on the left contact? What is F plus x equal to 0? So, F plus x equal to 0 will depend on the velocity of the charge carriers as well. So, this quantity is F plus x equal to L. F plus x equal to 0 will be number of excess charge carriers on the left contact times the velocity at which they are traveling, or this velocity is an interesting parameter here. This is also known as the unidirectional thermal velocity, because the net velocity of electrons is 0, typically 0, because if we consider that a flux is injected but almost half of that may scatter and come back. So, almost half electrons are traveling to the left side, half electrons are traveling to the right side, and that way the net velocity will be 0. But if we are only considering the flux going to the right side in one direction plus x direction, then we need to take this thing which is known as the unidirectional thermal velocity, which is the velocity of, which is just the velocity of electrons traveling in the plus x direction. And so, the flux at x equal to 0 will be n x equal to 0 times velocity, and we need to divide it by 2, because the number of electrons going to the right side is actually half. If we consider that half of them may scatter and come back to the left side. So, from Fick's law we have calculated the flux entering to the right contact. From our basic intuitive understanding, we know what is the flux at the left contact. So, we can find out the transmission coefficient as well, which is the flux entering the right contact divided by the flux of electrons at the left contact. So, it will be this by this. So, n and n cancel. What is left is dN divided by, or 2 dN divided by L times Vt. This will be the transmission coefficient. And if you remember that this dN, the diffusion constant, is generally LVT by 2, and this comes from the scattering theory, which we have not covered in this course, and possibly we won't be able to do that. But let's take it as it is, and if we put this, then this transmission coefficient in the diffusive limit becomes lambda Vt divided by LVT, V2 as well. So, T is essentially lambda by L, which we have also seen during our discussion on the general model of the transport. So, this is the transmission coefficient in the MOSFETs in diffusive limit. But if we consider the quasi ballistic limit, in which the channel length and the mean free path is of the same order, in that case this becomes lambda divided by lambda plus L. Okay, so this is just a quick refresher of the general model of transport and how we will use those equations in the context of the MOSFET. In the coming class, we will discuss this interesting parameter, this unidirectional thermal velocity, and then IV characteristics of the ballistic MOSFET, and we will also try to see how the current depends on the voltage in the case of ballistic MOSFET. Okay, so that's all for this class. Thank you for your attention and see you in the next class.